Welcome to a concise tour of language models, tracing how early rule-based systems evolved into today's GPT-style models. This slide lays out the broad arc visually, from grammar and expert systems to statistical models, neural networks, transformers, and finally generative contextual understanding. And it sets our analytical perspective on how our notion of understanding has shifted as architectures and scale changed. In this slide, we step back to the foundations. Saussure's structural linguistics framed language as a system of differences, giving later computational grammars a conceptual base, and the 1954 Georgetown IBM experiment showed machine translation was conceivable but brittle, lacking deep contextual understanding. Together, they illustrate how early theory and first experiments set the stage for later probabilistic and statistical approaches. This slide highlights the shift toward probabilistic NLP, showing two key milestones. Karen Speck-Jones's introduction of IDF to measure word importance across documents instead of raw counts, and IBM's Candide project, which used probabilistic models to learn translation probabilities automatically. The takeaway is that measurable statistics, not handcrafted rules, began driving language processing and enabled scalable learning from corpora. Here we look at n-gram models, the statistical backbone of the 1990 seconds, and why they mattered. N-grams provided simple predictive power for tasks like speech recognition and query prediction, but they struggled with data sparsity, requiring smoothing techniques like good Turing to assign non-zero probability to unseen sequences, and the emergence of traded trigram counts created the first widely available language resource for research and industry. This slide marks a pivotal moment. Neural language models rose by moving from count tables to distributed embeddings and hidden layers, and the GPU revolution made practical training possible. Continuous vector representations enabled semantic generalization beyond surface counts, while GPU acceleration in the mid-2000s revived deep learning and reunited machine learning with NLP, opening the door to powerful learned representations. Thomas Mikolov's 2013 work on word embeddings introduced simple, shallow architectures like CBOW and skipgram that produced dense word vectors encoding semantic relationships, famously illustrating analogies such as king minus man plus woman equals queen. These methods were scalable, trained quickly on billions of tokens, and became the default representation that downstream NLP systems relied on for efficient, transferable semantics. This slide covers the evolution from recurrent encoder-decoder networks to attention mechanisms. Early LSTM-based seek-to-seek models achieved state-of-the-art translation but were bottlenecked by a fixed-length context vector, while the Bahdanau attention mechanism allowed decoders to peek back at each source state, creating adaptive context vectors and foreshadowing the move toward full self-attention architectures that removed recurrent limitations. The transformer architecture represents a true paradigm shift by replacing recurrence with multi-head self-attention and feed-forward layers, enabling parallel training and capturing long-range dependencies more effectively. Positional encodings preserve order, while attention links positions directly, yielding a scalable blueprint for generative modeling and setting the stage for training on much larger corpora with far greater efficiency and capability. Google's BERT introduced bidirectional pre-training with masked tokens and popularized the pre-train then fine-tune paradigm. By masking inputs and forcing the model to fuse left and right context, BERT produced powerful contextual encoders that could be fine-tuned on downstream tasks to achieve record scores. This approach shifted practice across industry and academia toward leveraging large pre-trained checkpoints for many specific applications. The GPT series illustrates capability scaling through autoregressive prediction and alignment via human feedback. Larger models trained to predict next tokens demonstrated emergent abilities as parameters and data scaled, and reinforcement learning from human feedback helped align behavior with user intent. The result is versatile AI assistants capable of coding help, content creation, and conversation, emphasizing capability and utility scaling in modern systems. Recent advances focus on optimization and multimodal integration to converge efficiency and capability. Techniques like sparse mixture of experts, retrieval augmentation, and low-bit quantization reduce compute and memory while extending context, and multimodal pipelines combine vision, audio, and text encoders into unified reasoning engines, enabling models to understand and reason across images, sound, and code for richer, sensory-aware interfaces. The final slide addresses societal deployment and responsible innovation, highlighting alignment with human values, transparency reports, and regulation against misuse as governance imperatives, while research frontiers emphasize interpretability, data governance, and energy-efficient training. The slide also frames future implications, tools that can democratize access versus the risk of concentrated power, underscoring the need for historical literacy to steer technology toward beneficial outcomes.